Thank you, Tony, and thank you also for the large audience we already have in this webinar. I'm very happy to introduce and to have Guy with us, the ones who've been in the webinar with Guy together before, maybe recall of the content. Guy is one of the, I would say, the pioneer of human system integration and human-centered design, and he has a lot of experience in airspace and also in aviation general. So we are happy to have him because we see that the gap between automation and the human operator is spreading and it's getting larger, and it's important that we take over our responsibility and also role in the companies to close the gap a little bit. And I think Guy is the right person to guide us and also to give us and let us take part on his experience. So planned is a 4-time webinar with Guy, which is building on each other. Today we have the title Evolution of Automation. We will have one in October, the role of the human in complex systems. Another one this year is problem solving and reactions to unexpected situations. And the fourth one next year, beginning of next year, is about case studies. There will not be aviation, there will not be air traffic control studies, but there will be a lot of case studies where we easily can transfer the sense in it into our field. So I'm happy to have you, Guy. Happy that we have this large audience, and I would pass the word to you so that you can start your presentation. Thanks a lot.
Thank you, Jörg. Thank you, Tony, also to invite me. I'm going to share my screen, okay? Let's see. Can you see the first slide?
Yeah, looks good. Thank you. Thank you. Okay, go ahead.
Okay. Okay. So this talk today is about the evolution of automation, at least the way I see it. I'm actually leading a chair in Paris-Saclay University, Centrale Supélec, and also at Estia in the southwest of France. So check. So this lecture is the first of a series of 4, as was said before. And I will try to describe automation as departing from single agent perspective to a multi-agent. We see that later. Historically, I mean, we were looking at, you know, how to automate speed and altitude, or if I talk about aviation, and parameters one by one, and then we combine several parameters together, and then we incrementally augmented the number of variables and parameters, and now we are increasing the number of agents and interacting among each other. So my second lecture will be devoted to the human role in large complex systems. I've been involved in this for quite a long time now, and I will try to make a survey of that. The third lecture will be focusing on problem-solving support, and in fact, it's mostly in cases of unanticipated or unexpected event or situation, and these are situations where you need flexibility. In fact, when you use procedures and automation, you have some kind of rigidity because it's already planned in advance, and when the context is not fitting what the context of the design of these procedures and automata were designed, then you need flexibility, and this is really important to design the right technology, the right organization, and provide the right competence to the people. So the first lecture will be next year. I will illustrate all of this using some industrial projects I worked on during the last, I would say, 20 years. Okay, so and most importantly, I'm really working on human systems integration right now, and I will try to show, you know, the genesis of this discipline. So the outline of this talk is the following. So in fact, I will provide some you know, information on cockpit automation evolution, analysis of a few accidents. Well, we'll pass on this very quickly. Cognitive function analysis, human factors associated with automation, you know, this issue of human error and regulatory solutions and human-centered design and automation. You know, if we go back at the beginning of the 20th century, the last century, we started with very simple cockpits. Basically, no real automation there, and then we increased the number of instruments. Now we say embedded systems, but and then we increased this number of instruments with respect to three main criteria. The first one is safety, the second one is performance, and the third one is comfort. So if we continue, you know, I think the apogee was the Concorde. In the Concorde, you have 600 instruments in the cockpit for 3 people. And then after that, I mean, we multiplexed this, you know, the information, and we less instruments, but much more information. So this evolution could be summarized this way. In fact, from the beginning of the 20th century, we constantly saw an increase in the number of displays in particular, and then after that, a decrease. But that doesn't mean, as I said before, that the number of information decreased. There's the exact opposite. So we had to think about what to show to the pilots. We have incrementally increased information processing, in fact, in order to aggregate some useful information to present, to decrease workload, in particularly demanding flight phases, to provide the right understandable information at the right time, to enable pilots to react safer and more efficiently to situations, and also to enable pilots to delegate tasks to automation. You know, this issue of delegation will be a key issue during the 3 lectures I will provide. But the key point is the pilot remains the master of the operations. However, there are various ways to proceed with automation. You know, we have signals, information, and knowledge, and that we have to process. That led to several kinds of systems, and we can talk about multi-agent, you know, systems. Delegation became a very important topic. Cooperation and coordination. We now more and more cooperate with the machine. I recently wrote an article that is published in the Work Journal. The title is "The Machine as a Partner." And this is about human autonomy teaming. In fact, this is the evolution. So in fact, but all of this comes to a very important topic, that is situation awareness. We automate, we provide some more possibilities, capabilities, but are we aware of what is going on? That's the key question. So situation awareness requires to define what a situation is. What is a situation? So a situation, you know, you can see first, you know, these rectangles here. The real situation is very difficult to access. What you access is the available situation. the situation that is measured through sensors or through your eyes, you know, but the real situation is almost infinite number of parameters. So in fact, you have inside this real situation, you have available situation. And then it's not because it's available that you will perceive it. Then you have the perceived situation. And then it's not because you perceive something that you understand it. Then you have the comprehended situation that is more. And then there is another thing that what will you do with this situation? What is the meaning of this situation in order to act? The projected situation, you know, what you will do with that to act. Beside that, you have two other kinds of situation. The desired situation, what you want to do, you know, what you want, how do you want to transform the situation, and you have the expected situation, because we, you know, we deal with expertise there. Then you have a model in your head, and then you expect something to happen, and this is interesting because sometimes the perceived situation is actually the expected situation, because you don't really want to see what is really shown or heard, but it's what you expect. So in fact, all these kinds of definitions are extremely useful when you want to better understand human errors, or you know, how do you want to involve human operators in complex systems. So now I talked about situation awareness. Here is a model. This model is going to be published in a handbook that is going to be published at the end of the year. You know, the usual model of situation awareness is Micah Hensley's model, with perception, comprehension, and projection. Here, I want to use, you know, these definitions of the situations in order to improve the model of Micah Hensley. Then you have external sensors on the real situation that provides available situation. And then you have internal sensors, for instance, for the human is the eye and the hearing and this kind of thing, that are related to the expected situation. There is a model there in order to perceive things. And then you have the perceived situation. And then you have to interpret what is going on and comprehend what is going on. And then we have what we call the meaningful situation and the projection, the projected situation. Meaningful situation is actually the comprehended situation. And then all these, I mean, these two, interpretation, comprehension, and projection are directed by the desired situation, what you want to do. And then once you have the projected situation, then you can act and take action. But you have an overall, what we call the long-term memory background situation that actually provide some directions to these information processes in the head of the human operator. So I wanted to give you these models because they are extremely useful when you automate. Now, talking about evolution, I want to use, and most of you know the Rasmussen's model. James Rasmussen is during all his career, he worked on nuclear power plants, and he tried to model the human operators in nuclear power plants. And his model was used in aviation a lot, So in fact, I want to use this model to better understand the automation evolution. So if we start in the 1960s, you know, in the Rasmussen's model, we have the skill-based behavior, you know, the stimulus response. You know, you sense an information and then you immediately react and to produce, you know, it's like riding a bicycle, you know, or steering your car. This this human behavior, skill-based behavior, was automated on machines using electrical engineering, mechanical engineering, and control theories. All this was done much before the 1960s. In fact, the first autopilot was developed in the early 30s. I think it's 1932, the first Boeing airplane having this kind of automaton. So we transfer, you know, this cognitive function from the people into a machine using these disciplines. Then in the Rasmussen's model, if this level skill-based behavior doesn't work, because you need to think, you need to go to a cognitive state, then you have the rule-based behavior. You have to think and recognize the situation instead of automating the sensing and effecting. And then you have rules, you know, that if this situation is active, then is perceived, then I'm gonna apply this task or this procedure. This level was transferred to the machine using several disciplines related to automatic control and operations research, optimization, expert systems. You know, if the first level is related to autopilot, the second level is related to the FMS, for instance, the flight management system. So this transfer was made in the 1980s. Then, if you don't succeed, if you don't have the right rules here, you know, if you don't recognize the situation correctly, then you have to go to another level, to another level that is the knowledge-based behavior. You don't have these rules. You didn't learn these rules yet related to the situation that you perceive. And then you have to identify the situation. It means that you have to make sense of what is going on. You have to really think, highly think. And then once you have identified the situation, then you have to make a decision related to the goals that you have. And then you have to plan a series of action. You have to make procedures on the fly. This level was really worked during the 90s and 2000 in cognitive engineering, but using human and social sciences. This level was supposed to be taken into account by artificial intelligence, but unfortunately, you know, in the early 90s, we had these pilot associate programs, or you know, didn't work pretty well because we had problems to representing context mainly. And so today we have this issue of dealing with this level using artificial intelligence system support, but not necessarily automate that fully. So we have to see, you know, if you look at the car industry, you know, there are 5 levels of autonomy, they call that. And then, you know, level 5 is you have no steering wheel. You know, you are in the car and you can have a meeting and watch TV if you want. But at the moment, we can see that they are stuck at the level 3. And so that means that we need to have support for autonomy at this level. We'll come back on that. So in aviation, and I will talk about aircraft here, the first level, you know, the skill-based behavior, as I said before, was automated, and we developed, especially at Airbus, side stick and trust. This was the beginning of the 80s, mid 80s and late 80s. We automated this level. The time constant there was 500 milliseconds or something. And then we went to the second loop. Oh, by the way, I want to thank really my friend Etienne Tarnowski, who provided me this kind of schema a long time ago. We worked together. We were working together. So the second loop was the guidance automation. You know, where we introduced the FCU and on the Airbus aircraft, so we were dealing with autopilots and autothrottle and high-level modes. And then we went to the loop 3 with the navigation automation, really the FMS, where, you know, here we are talking about integration of guidance and flight management. You know, what we realized at this time, was the shift from control to management. Instead of controlling, you know, handling qualities, you know, flight parameters, we swapped to managing systems that are doing the job that the pilots was doing before. So in other words, this is a kind of delegation that we have done. Then we are entering into loop 4. Loop 4 is about automating the ATM. It's not totally done yet. But in fact, we start with a data link, and then I'm sure we're gonna improve these kind of things during the years to come. But here, this is another story. We have to deal with multi-agent systems, real multi-agent systems that we need to better understand. And I will try to make a point, especially during the next lecture. So one thing that I want to say is that we automated during I would say, the last 60 years or so. And we automated this way. In fact, if you take on the axis, you know, the levels of autonomy or automation autonomy, from the full human to full machine autonomy. Usually, and you put on the ordinate here the human machine system performance. When you automate, you know, the lower curve, when you automate, you increase the performance up to a point. After the point P0 here, after this point, you start to decrease the performance because the people don't understand really well what is going on, in fact. And the problem is, we have automated sometime, not all the time, but sometime, on this point here, which is the technological limitation point, where we automated the more we could, but that was too automated to understand. So in fact, we started to oscillate and come back to P0, but by doing this optimization, by using the system, we jumped into another curve here with the optimum here shifting towards more automation, in fact, okay? And then if you understand everything, of course, you can go to the full autonomy, but this is we are not there yet. In any case, you increase knowledge when you do that, when you start, because why? Because doing automation, you know, doing these automated systems, then you have to better understand, you know, what is going on in the physics of the flight, and then you have to make models and theories that improve your knowledge, in fact. So, but where is the human there? I wrote a book in 1998 called Cognitive Function Analysis. that where I developed the concept of a cognitive function. What is a cognitive function? So a cognitive function is for instance, is a cognitive function is following a heading, or trying to take a descent profile, or something like that. And so a function could be defined in two ways. The first way is the logical way. The logical way is, when you have a function, for instance, an application in mathematics, y is equal to f of x. Here, in this case, x is the task to be realized, to be executed, and y is the activity that you produce. So in fact, in between, you have a function, a cognitive function that transforms the task, the prescribed task, into an activity that is an effective task, in fact, what you have done, really. So we define that in this book, and we have used this thing tremendously to design Airbus cockpits, in fact. And then you have another definition that is teleological, where a function is a function of an agent in an agency. For instance, if you take a postman in the post, the agency, the post, as a function to distribute letters. Okay, so in fact, and this function is defined by its role, by its context of validity, and by the resources that are allocated to it. So in fact, all this has been defined to better understand automation. And I'm going to use it now. So a cognitive function, as I said before, is something that transforms a task into an activity defined by a role. Okay. For instance, if I take the postman, the role is to distribute letters. Okay. And context is from 8 to 12, and from 2 to 5, for instance, in France, 5 days a week. So this is the temporal context of definition of the role of this person, but also the neighborhood. This is the space context, but also the context could be normal or abnormal, and I will come back to that. And then the resources. The resources for the function could be physical, like the bag to transport the letters, the bicycle, car, whatever, but also cognitive resources, like, for instance, trying to pattern match the name of the street with the name of the street on the letter, the number on the door, and the name of the person on the letter. And so as I said before, resources could be physical and or cognitive. And in fact, this is interesting because cognitive resources are cognitive functions themselves. So in fact, this definition is recursive. And then you can, when you develop a cognitive function analysis, then you develop a graph of cognitive function that is very interesting to handle, because that provides, if you look carefully at this network of cognitive function, you can see the complexity of the operations. So if I take the cognitive function of a human, this one, and I have a machine here, and I transfer this cognitive function into the machine, like, for instance, remember when I use the Rasmussen's model, when we transfer some cognitive functions, skill-based behavior into the machine, making an autopilot, or transferring a rule-based system that is actually the navigation rules, for instance, transferring into the FMS, then you build. So of course, the functions on the human side are not necessarily the same as the one in the machine side, but they perform very similar tasks, And then the most important thing is well, first to design these new functions in the machine, which we call automation. But the most important thing is to better understand, or to to discover what I call the emergent functions coming from the use of this new cognitive function on the machine. So we need to look at this emergent function all the time. And we had problems in the beginning of the 90s. People in human factors were saying, well, automation is not so good because we are, we deal too much with surprises. We have surprise in the use of automation. But in fact, these surprises should be investigated, and it's better to investigate as early as possible in simulation, human-in-the-loop simulation, in order to figure out what are these emergent functions, in order to reconsider the transformation of the jobs. This is what we call human-centered automation, in fact. So, okay, let's go to the next slide. So, for instance, if I take an example, I talked about situation awareness, cognitive functions. These two screens here represent the same kind of events. On one side, you have the ground side, and on the right-hand side, you have the aircraft display. So, if we take this problem of the TCAS, for instance, the TCAS is a transponder on aircraft that provides information on the flying objects around the aircraft, and it's especially very useful when you have risk of collision. And these two TCAS, traffic alert and collision avoidance system, are programmed on one side to say climb, on the other side to say descent. So the thing is, this cognitive function in the head of the controller here, that is actually the separation, or conflict resolution thing, has been transferred in another way in the TCAS. So in fact, not only we transfer the authority from the ground to the aircraft when we did the TCAS, but also we transfer from a human to a machine. And then you have to look at the cognitive functions emerging from the use of this new system, this new function. And there are several kinds of emerging functions that you have to consider. All of this was not really well done, when we designed all this a long time ago. But we analyzed this, especially when we analyzed the Überlingen accident, where we realized actually this connection of emerging functions, and that actually provide, if you take the Überlingen accident, for instance, there should be a link, a physical link between the TCAS and the STCA, for instance. But I'm not sure this is done yet. But I didn't do aviation for quite a while now. I work on space and other things for almost 20 years. So we'll come back on that. If you have questions, I will be very happy to answer on this. So in fact, the concept here is the question of emergent cognitive functions that we need to discover. Something else now. We designed machines during the 20th century. We realized that there were people who were going to use these machines, and guess what we have done? We have designed the user interface. So the user interface is designed by, human factors. People realize what were the human factors involved in the use of the engineered system, but also ergonomics for the design of the interface and automation here. So for me, the user interface is a concept of the 20th century. This is something that we add to a machine in order to adapt the people to the machine. So I want to depart from this. I want to depart from this concept here and go to the 21st century. So to do that, let me tell you a story. This is my car when I was a student. I was a student super-héros in Toulouse. I had a deux chevaux, I don't know if we can say two horses in English, but deux chevaux, Citroën. And I was able to repair or clean the carburetor very easily. Very little electricity in it, only for the lights and the shock. So that was extremely simple. But the mechanics was not so simple. You have to understand, and if you unplug things, then you have to make it work again after that. So in fact, this was really hardware based. And during the end of the 20th century, we automated a lot this. So today we have these kind of things. Impossible to repair by yourself. You go to a garage, and then the guy comes and he has a tablet, plugs the USB socket under the steering wheel, usually, and then read the line and tells you how much it will cost. If you don't ask him what it is, because he will read another line and tell you what it is. So we shifted, the shift was during the 20th century. What we have done is we went from mechanical engineering to electronics and to software. We moved from hardware to software, and we accumulated software functions and hardware structures along the way. We automated, I put AI, artificial intelligence 1, because there is artificial intelligence 2 today, and HCI, human-computer interaction. All these were the disciplines that were developed in order to make these new systems, understand them, and assess them, evaluate them, validate them. So but what you have to remember here, 20th century, from hardware to software. Today, we do the exact opposite. From the beginning of the 21st century, we start designing an aircraft by, or all the things, by doing a model, a digital model, and a simulation, a human-in-the-loop simulation. In order, this is the Falcon 7X, in fact. So we, you can design the full aircraft as a piece of, a huge piece of software or pieces of software interconnected, and then you can design the user interface here, the cockpit, and test the system before anything is really concretely or tangibly built. So that's a very, very interesting thing from a human factors point of view, because you can test the activity before the system is built. Of course, you build something virtually, you have a virtual prototype, and we will see the problem with that. But from a human factors point of view, it's really great, because you don't limit yourself to task analysis, but you can do an activity analysis in the sense that you can start to discover these emerging functions, emerging cognitive functions. That's a big difference with the 20th century. So during the 21st century, we start from software. We have new stuff. The new stuff is modeling and simulation, digital modeling and simulation, virtual prototypes, connectivity. You have several systems, multi-agent that can interconnect. When I was in the United States, I had a lab with a two flight simulator, an Airbus A320 and a Boeing 737, where we were connected with the air traffic control and the weather forecast and things like this. So in fact, all this was simulated. And then we designed some new instruments within the complexity of the interconnected multi-agent systems. The problem was to orchestrate all this. So it's not a very easy task, but we can manage to do it. And then we dealt with data science and cognitive science. And then incrementally with 3D printing, this industry 4.0 we are talking about. So we inverted the approach from of the 20th century that was from hardware to software. Now we are going from software to hardware. So the question is, we are using new kinds of algorithms using AI today, AI2, HCI, and virtual human-centered design that involves human-in-the-loop simulations. But very importantly, one of the things that emerged from this new approach is the tangibility issue. Tangibility means, is this virtual prototype, are these virtual prototypes tangible enough to believe in the result that we have when we try to make sense of these emerging cognitive functions? So I will come back on tangibility. But before, I want to show that, in design, and this is, I talked about aircraft cockpits because I'm familiar with that, but that would be very valuable for ATM, ATC systems. We have worked with nuclear power plant people. We have worked with the car industry. We have worked, at the moment, I'm very tight to the French Air Force. So we are working on the FCAS, the future, air combat system. This is very generic. This is coming from NASA, by the way. So we are okay. When you put on the axis, the development phases of a system. You start with the design, then manufacturing, then certification, then operations and support, and dismantling in the end. Not to forget, because sometimes when you forget, it costs a lot of money for the generations to come. So if you with this technology-centered approach that we had until very recently, if you look at the red curve, the resource commitment, we usually commit too early. This is due to the fact that the manufacturers are connected to suppliers that have these systems, in their shop, if I can say this way. And then we commit too early. That means that if you commit too early to resources for the development of a complex system, then the design flexibility drops very quickly also. So in fact, you come to a point where you cannot do much because it's rigid now, And then the system knowledge, you learn about the use of the system or the way the system behaves and the way the system can be used by using it, in fact. And in fact, the green curve, provides the evolution of this system knowledge, So now, if we do what I said before, human-centered design, where we put modeling and simulation, human-in-the-loop simulation, very early, then, in a virtual environment, then you can learn very early about systems knowledge. With the tangibility issue, of course, that you have to consider, because we have to make more progress on how to measure that. I will come back. So, and then the design flexibility, if you look at these curves, the concavity is inverted, in fact, because you can spend more time being flexible because software can be modified very, very quickly, sometimes too quickly, because we could have erratic approaches. And the commitment of the resources is also inverting, concavity wise. So in fact, this is important to consider that. In industry, this issue of flexibility is extremely important. Now, if I take this, this modeling and simulation, and I put that during the whole life cycle, we do that with at the moment with an engine manufacturer in France for maintenance issues. So in other words, we develop a digital twin. This modeling and simulation is a digital twin of engines, for instance. So in fact, if I come back to the diagram here, I increase, this the scope of this modeling and simulation, and I call that a digital twin. So digital twin is actually the image of the system in a digital mode. So in other words, we expand the concept of human in the loop simulation, HITLS. But we put that during the whole life cycle, and that's very important because we can test the what if. What would happen if I do this? In maintenance, for instance, they try to realize what the people have done to break an engine, and so in fact they can test the what ifs. This is also a vivid documentation, in the way that it's no longer paper, but is MBSE, model-based system engineering kind of thing, and but where you can integrate experience feedback. So in fact, these digital twins can be improved by using them and by using the system itself. This is a kind of organizational memory. So in the end, digital twins can be considered as a virtual assistant. This is where probably autonomy will come from. When we talk about human-machine teaming, it's about multi-agent collaboration. Where you have this image of the system that could be provided as a brain, if you want, that could be used for collaborative work with the system itself. So now, summarizing. 20th century, we went from means to purpose. First, we designed the machine, and then, unfortunately, sometimes we try to figure out how to use it. So we started with engineering. We realized that there were people using this, and then we put user interface in between. This is one of them, the cockpit, but there are many others. So in other words, if I make that more generic, we have a physical environment that we have designed, people that will actually use this physical environment, and then in between, a control and management space. Disciplines, this approach I call inside out. We go from the kernel of the system to the use of it, the users. Engineering, ergonomics, HCI, and automation were disciplines. Now, 21st century, we have an opposite approach. It's not from means to purpose, but from purpose to means. Because we can do that because we have these virtual environments. And we could have an outside-in approach where we can start from the task analysis and then incrementally activity analysis and etc. And then design the system taking into account emergent functions and structures. But we have to consider that incrementally you have to tangibilize these kind of things. So I pass quickly on this, but this is what we mean by HSI, Human Systems Integration. Now, what do we mean by tangibility? Tangibility could be understood in two ways. First way is physical tangibility. I hold my pencil here. I grab my pencil. This is an object, a physical object. This is tangible. I grab it. And now I try to convince you, and I hope that you're convinced, and you say, well, what you're saying is tangible. It means that I can grab the concept. I can grab the abstraction. Today, with this approach of virtual prototypes and taking into account the virtual prototypes to get these emergent functions, then the tangibility is more and more important to consider. This is why we are developing metrics for that. I have no time in this lecture to provide you with this, but I wrote a book in 2016 called Tangible Interactive Systems. You have 220 pages on this. Second is the virtual prototyping and human-in-the-loop simulation that is very important and this is coming from there. So in fact, the tangibility is coming from the virtual. My book, 2020 book, is called Human System Integration from Virtual to Tangible. And the third point is from purpose to means instead of the usual opposite, where you have to consider, these tangibility issues. So this is the book, by the way. I made a slide. I thought I would avoid that, but these are the 5 metrics that we have developed: complexity, maturity, flexibility, stability, resilience, and sustainability, to make sense of what tangibility is about. One thing that I would like to emphasize is the maturity. We usually talk about TRL, technology readiness levels, but you have to consider also 2 other ones: the human readiness levels and the organizational readiness level at the same time. So in fact, I will not develop all these metrics here, but you have that in the book here. Something that you have to consider at the same time are social factors like shared situation awareness, cooperative decision making, harmonized risk taking, and trust and collaboration. We have published recently an article on trust and collaboration that you're very welcome to get if you want. So now let's look at these maturity issues. So this scale here was developed at NASA quite a while ago now, it's in the 90s, TRL, that is being used all over the world for technology. But this is not enough. We need to consider these human readiness levels as well. These HRL's descriptions here come from the US Air Force, in fact. And we are developing our own currently here in France. Another set of readiness levels are the organizational readiness levels. This is an example of what we have done recently. I also have a paper on this. If you're interested, you can ask me and I will send it to you on ORLs. Because when you develop a new technology, you need to measure, the evolution of the organization as well, and how to design the organization is a topic of another lecture. So in fact, to summarize, maturity is about incremental adaptation. Adaptation of technology, this we know. We have adaptation of the organization, that's adaptation of people. So this is okay. But there is no adaptation without risk. And this risk can be legal and operational, psychological and law related. You need to prepare the risky operations. So in fact, that's, again, these human-in-the-loop simulations are extremely useful for that. Responsibilities at stake, individual and collective risk have to be considered, and organizational risk as well. So in fact, all this is being studied right now. So now, for doing this, we need a method, or we need methods plural, of course. So this is going to be the topic of my next 2 lectures. In fact, I introduced this. Next time, we will present the product method that supports human system integration. And we recently published that. This method cannot be used without a deeper understanding of what HSI is about. This is why I'm going to introduce that next time. And HSI will then be further presented in, this is what I just said, during the next lectures. So these are my references, the books that I wrote actually, and my presentation is based on these books. Cognitive Function Analysis in 1998, the Handbook of Human-Machine Interaction, that was 2011, and Orchestrating Human-Centered Design was in 2013, and Human System Integration in 2020. And of course, be curious. Look at other references. I mean, my lecture is based on the work I've done, so this is why I mentioned these books. Thank you very much for your attention. I'm open to questions.
Yeah, thank you very much for this interesting lecture on the history of automation. Also, I like very much how you bring together the technology, humans, and organization. And there are just a handful of questions before I read them from you from the Q&A, and I encourage the colleagues who are still in the webinar. We have still about 10-15 minutes to address few questions to Guy. In this history of automation, we usually automated the tasks which are easy to be automated, and we let those who are very, very difficult outside that. Are we reaching these levels of bringing together, technology, human, and having human integrated with technology and organization, sorting that problem? Because also in the age of, I would say today, of machine learning, AI, the automation, the things are happening faster and faster and faster. And now one of our issues as humans, you are losing control. And also with the automation, we always have this irony of automation. Are we capable of fixing these problems, or is there light at the end of the tunnel if we work as you suggested? I know it's maybe a theme for a webinar there, but just briefly.
There are several questions in this question, but I try. Yes, we automated easy tasks in the beginning because it was easy to do. I mean, easier than the others. But incrementally, we accumulated, automation, layers and layers and layers of automation. And we separated people from the real phenomena, the physical things. So that's this is why the question of situational awareness came up. We need to understand what we're doing, and sometimes you don't need, because when it's fully understood, it's like, for instance, if you take a computer. In the beginning of computer science, I remember when I was a student, we had computers that I was developing some software, and we developed software at the level of the machine, assembly language, or so the user and the engineer and the programmer were the same people. Today we have several layers of automation, in these computers. Nobody using when I use the computer to provide this lecture, I don't know what is going on inside. And more than that, I don't want to know, but all this is now mature enough to, technologically mature. So in fact, the maturity is really a very important factor, because maturity will determine if you need to understand what is inside or not. This is important. This is the same for the cars, for instance. In the beginning of the car industry, then the driver, called the chauffeur, was actually like the coach in the past. The owner of the car was in the back, and the driver was very knowledgeable in mechanics. At the end of the 20th century, very few people knew what was going on in the engine of the car, and didn't want to know, actually, most of them. So, in fact, this is related to maturity. But there are other kinds of maturities, as I said. The human readiness levels, the maturity of practice, if you want. So there are things that we need to better understand when you practice. A car, for instance, could be a racing car or a truck. This is not for the same usage. The purpose is different. And then we specialize. We tend to specialize incrementally, this automation. So, and this is the same for organizations. We end up, but I don't want to give the next lecture here. We develop three kinds of model for organization. I will tell you that next.
I agree. Yeah. And I think one of the kind requests from the participants, if you can share the article on the organization readiness levels.
Yeah.
if we have that from you, I'll distribute it.
Sure.
The next question is as following. He said, from Indra Sudarsano, he said to Professor Guy, I want to ask about security. If all equipments controlled by system in the future, actually, I quite a bit worry about that, because there is an authorized person intercept to that system so that he cannot control it as far as he can. So what about the, I guess, the interference? I guess you will treat it as another agent into this integration of the cyber part of it.
Yeah, when you talk about security, it's not safety. I mean, it's cyber security, right?
Yep.
Okay, so, well, this is related to the evolution of data-driven systems, you know, and you know, we are the fact that we are more and more in virtual world, and then of course, I mean, the security, the cyber security is a very crucial topic. In my lecture, I'm sorry, but I will not cover this part of the cyber security. This is the topic of it's another type of lectures I could give, but I decided not to do it. So to further explain what we can do in this, and again, I mean, I'm not the kind of specialist you should have for that. I worked with people in cybersecurity when I was in the United States at NASA, especially, and we need to, you know, to protect yourself, you have to make sure that you don't provide data to the others sometimes. And so, in fact, this is a problem. And but on the other hand, if you want to be helped, you have to provide data. So this is a catch-22 problem. You know, this is a if we develop this cloud system, you know, in the Air Force right now, there is this trend of developing the combat cloud. You know, the enemy will actually try to discover, you know, how to attack this combat cloud. You know, this is another thing. It's not only the aircraft, but the combat cloud. So yes, there is this kind of issue, but honestly, I prefer to be modest on this and say, well, this is not my topic right now.
Enough, we move to the question of Madver. He said, how do you formally integrate humans, and especially the cognitive and social layers, in what-if models of digital twins? How does model can predict how a human agent will make a decision in a particular specific situation?
This is a good question. Okay, I'm going to answer with a story. I mean, I've been involved in the development of human models, human cognitive models for a long time. I know what you know, what you know, at NASA Ames, for instance, they have developed this Midas cognitive model for 20 years. I don't know how many people, probably 20 people. It's a lots of work. I mean, really lots of work. But in the end, this model was so complex that we need models to understand it. So the point is, I have right now, you know, my position is it's better to do human-in-the-loop simulation where real humans to discover these emerging functions that comes from the interaction between the guy, I mean a person, and a simulated system. You know, this is when you do that during design. Of course, when you have developed the system, it's directly the system, but these human-in-the-loop simulation are really, really important. And it's better than, we need cognitive models, but you need to stay, I would not say as simple as possible, but as crisp as possible on the analysis, in fact. And if you enter into very, very complex system, I mean, the complex system meaning the model of the human, it's extremely difficult. So I prefer human-in-the-loop simulation right now, after 42 years of investigation in this field.
Thank you, Guy. A few more questions. The next one is from Giovan Perot. The role of the concept of live virtual constructives are fundamental, but how important is it to know how to design both with available resources and with future resources?
Well, could you say the beginning? I didn't hear really.
The role of, yeah, I'll repeat it. So the role of the concepts of live virtual constructives are fundamental. But how important is to know how to design both with available resources and with future resources?
Well, it's important to, you know, it's difficult and most of the time impossible to predict the future. Okay, prediction is a short-term concept. You know, you can predict what in the short term, but in the long term, very difficult. On the other hand, you can anticipate. You know, like science fiction, you can anticipate. You know, like Jules Verne run around the world in 80 days. Well, we have done it in 40 days right now. And in the space station, you do it in 90 minutes. Well, you can contest this as an example, but you can anticipate some worlds and then test them in simulation. This is better than trying to predict some parameters. You know, this is but the problem is probably more expensive, but in the first place. But the money you will spend in trying to investigate if it works, you know, and trying to discover these emerging functions, you will gain a lot in the end. You know, we will have never went. We went to the moon in the 60s, late 60s, beginning of 70s. The people in the Apollo program made a lot of simulation. You know, they tried to invest. You know, they tried to figure out. You know, they could predict the space physics and things like this. So all this was great, but there were some parts, you know, related to people that were extremely difficult to predict and even impossible. So in fact, they tried to create environments where you know, they could simulate some stuff. And then you know, if you remember this Apollo 13 movie, where they actually were really prepared, not to prepare to solve the problem they had to solve, because that was difficult to anticipate, you know, this CO2 problem. But they had the means, you know, to involve engineers on the ground and build this CO2 remover and send the procedure to make it to the astronauts, and they managed to do it. You know, that's this is what I call flexible stuff. You know, you have to solve the problem during the flight, and so today we are entering into these kind of things. You know, because everything is so interconnected, it's so complex and difficult to predict sometimes, that you have to provide this kind of approaches that I call FlexTech, in fact.
Thank you, Guy. And the last question for this webinar. It comes from an anonymous attendee, but I still think it's an interesting question. The person says, I completely understand the concept of human-centered design, but as aviation is a global industry, how do we address the following issue? How do the concept mentioned in this talk address such challenges? For example, we design an aircraft or systems with warning indicators in red color. However, they are sold and used by all countries around the world, where red means different things in X country than in many other Western countries. Well, the country was China. But let's say it's culture. Well, in different countries, the colors means different things probably. So how do we make it, because aviation is global?
Okay, this issue of cultures is a recurrent question. In fact, yes, we have different cultures. We have different, I would say, affordances. You know, we don't react to objects or technology the same in one country and in another. So there are several solutions for that. One is standardization. You know, if you take the smartphones, whenever you go on this planet, everybody has a smartphone, and we have standardized this communication. It's really incredible. In a few weeks, I mean, the people do that. You know, that's and a few hours. I mean, it's so in fact, standardization is one solution. but the people may resist to standardization in the sense that if the red color doesn't mean the same, in one country and the other, which I know, I mean, it's because of the affordance. The affordance is a concept that means the relationship between an object and a human. The affordance means afford to do something. You have an object that affords to do something. So if the red affords you to stop, it's not the same as if the red affords you to go. So yes, sure, but you can learn. When I go to England, I have to drive on the other side of the road. So it's yes, it's there are affordances and there are I would say norms, standards, and so. I don't know what to answer besides of that.
No, I think it's a good answer. Thank you very much. And I promised was the last one. There is still one last from Rigiera. It says in ITIL framework there is a PDCA cycle, plan, do, check, and act. We have the feedback after deployment. So in that ITIL framework, the PDCA cycle is the feedback after deployment. In organizational readiness level, seems the end is the deployment. Is it true, or what's your view on that?
Well, if you wait too late, you're going to have lots of problems. This is why we promote human-in-the-loop simulation from the beginning. The problem is financial there. We have to be convinced that it's helpful. The people who decide, the top management. So in fact, this kind of approach is very important. So there are many examples where we came to failures because we didn't anticipate early enough, some emergent functions and structures. And the best way to do it is to do simulation, human-in-the-loop simulation. Otherwise, I mean, you have to wait that everything is built, and then you start the flight test and you realize, But what is interesting is that, this virtual flight test anticipate a lot of things for the real flight test, the physical flight test, and they may actually reduce the number of hours in flight test. In fact, so that's. After that, this is, but I think we will not be back to the past. I mean, I think we are immensely immersed into Industry 4.0, and now we tend to talk about Industry 5.0, where people need to be involved from the beginning of design.
Thank you, Guy. I think that actually makes an amazing point for this webinar, and we'll put the point there. I think on behalf of our organizing team and also from the webinar participants, we'll give you a virtual round of applause. So thank you very much for that. And I invite everyone to join us in 3 weeks. It's 3 weeks and a day from now. So the next webinar with Guy is on 11th of October, same time, 1500 Central European time. And in about an hour and 15, like today, he will dwell on the role of people in the interconnected systems, human element in the large complex system. So with that, we leave you here and see you in a few weeks' time. Thank you very much.
Thank you.